Greetings. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Today, our focus is the universe, specifically the causes and consequences of some immense cosmic explosions. Our guest is Berger, professor of astronomy at Harvard University. Dr. Berger specializes in really, really big cosmic explosions and mergers, the kind that produce detectable gravity waves and also the heavy elements such as gold. We are very pleased to welcome Dr. Berger. Thank you, sir, for joining us.
Oh, it's my pleasure. Thank you for having me.
And I'd like to just start by asking if you would please explain what are gravity waves. There was such a big deal when we finally detected these things. So I would like to get the background first. What are gravitational waves, if you prefer, and then why are they so hard to detect?
Yeah, this is an excellent question. So the idea of gravitational waves comes out of Einstein's general theory of relativity, which he formulated in the early 20th century. And when he came up with this new theory of gravity, which placed it in a very different context than how Newton formulated gravity, the idea of gravitational waves came out of the theory directly. Essentially, what gravitational waves are disturbances in space-time itself that travel as waves. By analogy, we can think about this as throwing a rock into a pond and then seeing the ripples of water that emanate from where the rock hits the water. Something similar happens for gravity. When massive objects accelerate through space-time, they generate gravitational waves that then travel through space-time itself. So for example, when the Earth orbits around the sun, both of the Earth and the sun are moving and generating gravitational waves, incredibly weak gravitational waves.
Just on that, why are they so weak? Then we'll just find out about what it takes to pick these things up and why that was a great triumph. But why are they so weak? They're all around, right?
Yes, they are all around us. From every object in the universe that is experiencing acceleration generates gravitational waves. The reason they are so weak is that the force of gravity itself is a weak force.
I see.
And so even though objects like the Earth and the sun, for example, generate gravitational waves as the Earth and sun orbit around the center of mass, those waves are incredibly weak. The way we overcome this is objects that are more massive and more compact generate stronger gravitational waves.
I see. So they got to be big in order to get them. And then it was a very big technological thing to develop the kinds of equipment that could pick them up. Would you please tell us a little bit about that and why the two mechanisms, LIGO and Virgo, and just how incredibly complex these things are?
Yeah, so to kind of place things in context, if we think about detecting gravitational waves from astrophysical sources, of course, those sources are going to be located at astronomical distances, no pun intended. And so the gravitational waves are going to be incredibly weak. To give an analogy, the strength of gravitational waves, or the signal that gravitational waves produce on Earth from these very distant cosmic objects, would be the equivalent of measuring the distance to the nearest stars to the width of a human hair.
Wow.
So this requires incredibly precise machines to measure these very small disturbances and displacements in space-time that are caused by gravitational waves that pass through the Earth. In order to do this, the idea that has gained favor and has actually worked in directly detecting gravitational waves is what's called a gravitational wave laser interferometer, which is the technology that's used in the LIGO and Virgo facilities. Essentially, those facilities are composed of an L-shaped arrangement of two arms that are precisely the same length. And a laser beam is shot into both arms. It reflects off of mirrors at the end of the arms and comes back and interferes, and the signal disappears. However, when a gravitational wave passes through, the effect of it is to first stretch and then compress each one of these arms by this minute amount that's equivalent to the width of a human hair at the distance of the nearest stars. And that small displacement has to be measured by the instrument. And they've actually managed to do that by looking at the laser light essentially coming back out of sync between the two arms. The amount of displacement can be measured, and the properties of the source that generated the gravitational waves can therefore be inferred from that signal.
Well, that's quite something, that to have those two mechanisms very far apart and having to confirm in this way against other background noise, I guess, in the universe is quite something. I remember being just so excited when this, the first announcement was made several years ago, and now people are really on top of this, really have this down. Okay, so the next thing is when you capture the, you record the gravity wave, then after that, could you please tell us, well, how you determine the source and location of the actual wave before we get into these big explosion things?
Yes, of course. So just like any other wave, a gravitational wave is characterized by an amplitude and a phase. And the exciting part about the sources that generate these gravitational waves is they're really captured in the final moments of their evolution, where two objects essentially spiral into each other, and the shape of the wave changes with time until those two objects collide and merge into a single object. And so by measuring the strength of the signal as well as its time evolution in the last few seconds in the evolution of these sources, we can then work back to the distance to these events, how massive they were, the ratio between the masses of the two objects. And there are many other properties of these objects that are encoded, how rapidly they were spinning before they merged together. And then by taking the signal that's measured by different gravitational waves detectors across the world, it is possible to triangulate the location of the source in the sky. And so this is the same way that our eyes work by triangulating an object and inferring its distance. The gravitational wave detectors essentially look at the arrival time of gravitational waves in each one of these detectors and back calculating where on the sky the event occurred.
That's very helpful, and it must be just huge fun for astronomers these days, with that, just detecting where these things came from, and then to just make sure that we understand on this side that it takes a really big explosion or Berger, as you call it, that to detect that, just because the gravitational waves are so weak, right? Okay, then these things, from what you have said, they before elsewhere, that these reveal a lot actually about the universe. It's not just the fun of capturing the waves, it's what they reveal. Could you please tell us? I remember, for example, your reference to Hubble's constant, and if you could include some of that stuff.
Yeah, so I think the really exciting part about the discovery of gravitational waves, beyond the confirmation of Einstein's general theory of relativity, is really that gravitational waves are a completely new tool of studying the universe. So the entire history of humanity, and including modern astronomy, the only way we've had until recently to study the universe is through light. Whether it's visible light or X-rays or radio waves, those are all forms of light. And that was our way of studying the universe. But that means that the only objects we can study are ones that emit light, some form of
Mm.
light. Whereas now with gravitational waves, we can see objects that until now were completely invisible to us. So
Ah,
we are seeing, for example, the collisions of black holes. And the
yes.
only thing that emerges out of a process like that, which is incredibly powerful, incredibly interesting, is gravitational waves. So now that we have this ability to see the universe in gravitational waves, we are suddenly seeing all of this exciting processes that are happening out there that were completely invisible to us. And we could only theorize about them, but we couldn't see them directly. So I think that's one element of this excitement, is just being able to see the universe in a completely different way. Not only that, even for certain processes that we have seen before, for example, supernova explosions, where we've seen hundreds and thousands of supernova explosions
Mhm.
before, but we never get to see what happens in the center of the supernova. That is
Yeah.
completely invisible to us. And yet, with gravitational waves in the future, we hope that we can peer all the way into the center of a collapsing star in the
Oh,
final milliseconds of its life and see exactly what is happening in the core of that star. Because gravitational waves can just travel through any amount of material. They are not blocked by anything. And so it's just a completely new way of seeing the universe. And then it offers us possibilities like measuring the expansion rate of the universe, the Hubble,
yes.
which we have now done in several different ways, but using sources that emit gravitational waves, in particular collisions of neutron stars that produce both gravitational waves and light. We can actually use a combination of the gravitational wave signal and the light signal to measure the expansion history of the universe and have a completely new independent way of measuring the Hubble constant.
Wow. It's very, so you've got a whole new, very expansive tool here, or a way of really examining, I guess, in greater depth, some of these phenomena in the universe that have been a little harder to judge, like the Hubble constant, maybe a unified theory. I'm not sure about that. In any case, you just alluded to some light also. And when you mention the black hole collisions, presumably do not give off light. So all that you have is a gravitational wave. But with the neutron star collision, or they say so politely merger, which sounds kind and gentle, you know, I have my doubts in the merger of neutron stars, you had light, correct? And that gives you some extra dimension to, what's the real glory of that?
Yeah, I think that these sources, the collisions of two neutron stars, or a system that so far we have not seen definitively, a neutron star merging into a black hole. There is the possibility
Ah,
of light being produced in that process, and the combined information from the gravitational wave signal that gives us something we've never seen before, direct information about the properties of the neutron stars themselves, and then the light signal, which tells us about what happens after that collision. Once the gravitational wave signal is done and the two objects have converged into a single object, presumably a newly born black hole, what happens after that point? There is material that's ejected from that collision. That collision is incredibly violent. It happens at about 1/3 the speed of light. And these two objects
wow.
are, yeah, these are two objects that are about the size of the city of Boston. They weigh more than
Yeah.
the sun. They collide at 1/3 the speed of light. There is material that gets spewed out in that collision. And the light information tells us about that properties of that material. And the gravitational wave signal tells us about the properties of the objects that collided. So when we combine these two things together, it gives us this just completely, 360-degree view of these very catastrophic collisions and about the birth of black holes, which is in and of itself a really interesting
Right.
process.
Yeah, that's fabulous. Since you mentioned this sort of detritus, the phenomena of what's left over from the collisions, and I think you have a particular interest in that. Could you give us a little more background about these weird stars, neutron stars, maybe magnetars, pulsars, these kinds of stars that you're really fond of, and their explosions, which evidently are, I was going to say a gold mine, that too, but I meant a gold mine of information. Why the great interest? What do they give you, these stars?
Yeah, so neutron stars are essentially the remnants of supernova explosions of very massive stars. So stars that are about more massive than 8 times the mass of the sun, will end their lives in a very different way than our sun. Our sun will kind of gently transform into a white dwarf at the end of its life. But these very massive stars eventually form these iron cores that weigh more than our sun, and are essentially unstable. And so at the end of their lives, those stars essentially collapse and explode in supernova explosions, and they leave behind these very dense remnants called neutron stars. So as I mentioned, these neutron stars are the size of a city, essentially,
Yeah.
on Earth, and yet they weigh more than our sun. So they're incredibly dense. They're heavily composed of neutrons. And there's been a lot of interest in neutron stars over the decades, because neutron stars sometimes show up as pulsars, these radio sources that act like lighthouses, sending these pulses of radio emission
Yeah.
towards us. And those turn out to be the most precise clocks in the universe.
Isn't that interesting? Yeah.
Yeah, it's amazing. And sometimes they show up as magnetars. So magnetars are neutron stars that are heavily magnetized. And those can produce incredibly large outbursts of radiation. And they've been implicated in a lot of interesting astrophysical phenomena. And sometimes these neutron stars are born in pairs. And those are the ones that are incredibly interesting from the point of view of gravitational waves, because those two neutron stars over their lifetimes, once both of them have formed, will spiral into each other as they lose energy to gravitational wave radiation, and eventually they will collide. And one of the reasons I find these sources particularly interesting is I've been interested for a long time, since the days of my PhD thesis, in the origin of gamma ray bursts. And
Yes.
one of the interesting theories that has circulated around for a long time in that field is that some gamma ray bursts are caused by the collisions of neutron stars. And I spent the better part of a decade of my research trying to find observational evidence for that picture. And we have found that there are a lot of these different properties of this subset of gamma ray bursts that really do point to collisions of neutron stars as the source of these events. And really with the detection, the gravitational wave detection of the first neutron star collision, we in fact saw a gamma ray burst happening at the
Ah,
same time as the neutron star collision. And that was really the final definitive proof that these two type of events are actually caused by the same type of phenomena, by the collision of neutron stars.
well, Dr. Berger, I think you have said neutron stars are collisions. Well, there may not be every 5 minutes, but they're not extremely rare, but gamma ray bursts are. Is that correct?
So both are the gamma ray bursts are more rare than the neutron star collisions, and the reason is that when a neutron star collision leads to a gamma ray burst, the burst of gamma ray radiation is beamed in a very narrow cone,
Ah,
and we have to fortuitously be in the line of that cone to see a gamma ray burst. One time out of 100 that happens, and the other 99 times those
right.
cones are pointed somewhere else.
I
And we could see the neutron star collision in gravitational waves and yet miss the burst of gamma ray radiation.
Thank you for clarifying that, because I haven't been able to understand that, but now that makes perfect sense. Just because these things happen doesn't mean you catch the whole thing. That's of great interest, and the gamma ray bursts are of great interest because you can't always catch them then. So there is that. And then you had another interesting idea about neutron star collisions and the fact that all that stuff that's left over that is of such interest to astronomers, that among that stuff is are heavy elements like gold, which we thought, I mean, I guess we've been thinking for all this time that these come out of supernova, but explosions. So could you help us understand why you have to have a super explosion in order to get heavy elements, and then why in these neutron stars that may be the case? And
Yeah, so I'll take it back one step, and I'll say that
yeah.
the question of the origin of different chemical elements in the periodic table has been something that's been of great interest in the astronomy community for many decades. And it turns out that different elements in the periodic table are formed predominantly in different kinds of processes in the universe. So for example, hydrogen and helium formed primarily in the Big Bang or right after the Big Bang. Elements like carbon and nitrogen and oxygen, the kind of light elements, form in the cores of stars like our own sun. And then they get recycled back out into the cosmic gas that other stars are formed from. The heavier elements, things like cobalt and iron and nickel, are known to form in supernova explosions. And so that's kind of the predominant mechanism where those are formed. And then there's been this long-standing question since the 1950s. So this kind of general picture was already known in the 1950s. And there was this question of, what about heavier elements? Essentially, that half of the periodic table beyond iron and nickel and cobalt was just assumed to also form in supernova explosions. And the fact is that we've actually never seen the signature of formation of these heavy elements, as you mentioned, like gold or uranium, the lanthanide elements, a lot of these very rare heavy elements. We've never actually seen the signature of formation of these elements in a super explosion, but it was assumed that because those explosions are so energetic and they form things like iron, then they must also form these other trace elements. But over the years, there emerged this alternative explanation where these elements could form in these neutron star collisions. And the reason that's a kind of exciting and attractive idea is that these heavier elements contain larger and larger fractions of neutrons in their nuclei. In order to form them, they need to form in environments where they start from lighter seed nuclei and get bombarded by a large number of neutrons. And so the question is, where in the universe could this kind of process occur? And of course, the one thing that comes to mind is if you collide two neutron stars, then the material that's spewed out of these neutron stars will be rich in neutrons. The problem there was that we've never definitively seen a neutron star collision, something that we knew to be a neutron star collision, where we could say, here is a neutron star collision, and let's go see if we see evidence for the formation of these elements. Until 2017, when the first neutron star collision was discovered by LIGO and Virgo. And we did extensive follow-up observations of that collision using optical visible light and infrared telescopes. And we saw directly the predicted signature of formation of these very heavy elements. And in fact, in quite a large enough quantity that when we take the rate of occurrence of collisions of neutron stars in the universe and how much of that material is produced in each one of those collisions, it can account for essentially all of the heavy elements, the inventory of heavy elements in the universe. Our conclusion is that, at least based on what we know now, all the gold, uranium, platinum, lanthanide materials, these kind of elements come from these neutron star collisions, not from supernova explosions.
That's quite a correction. That's an accomplishment all by itself, I guess. So the other thing then is that so these produce these heavy elements, and finding out, because they are so rare, and I suppose then there's a lot of interest in how these get recycled, distributed around the universe, and end up in gold mines on the Earth and things like that. But in any case, thank you very much for getting that clarified. Now I'd like to switch to you specifically. You have had quite a stellar career. So I wonder, you've done so many interesting things, and at just exactly the right moment in history, it seems like you're just right there. Could you please tell us something about your favorite accomplishments, your particular interests, and your favorite accomplishments?
Yeah, I can share a couple of stories. I think one will be from very early in my career when I was just in the first year of graduate school, and I think it's something that really left an indelible expression on me. So my interest in astronomy have go back to when I was around 10 years old.
I believe it.
And I've always been fascinated, I think, like a lot of people, in the universe and the big questions of where we come from and how big is the universe and what are all these points of light up there. And I've decided to pursue that as my career. But when I was in my first year of graduate school, I accidentally discovered, partly through, I think, taking some risky observations, I discovered the first object, a brown dwarf, which is an object that's intermediate between a planet and a star. The first one of those that produced radio waves. And that was a signature of magnetic fields on these objects, which were thought to be completely inert and inactive.
Wow.
And the reason I'm telling the story is that a lot of people have been studying these objects, people who are much more senior than me and were much more experienced in the study of these objects in astronomy in general. And they missed out on this because I think they had a preconceived notion of what these objects are and are not capable of doing. And I think that for me, coming into it with kind of fresh eyes, and willing to kind of take a risk and then recognize that there was something really unusual there that was worth pursuing and investigating, made a big difference. And so that left an indelible expression on me in the sense that both, as scientists, we need to kind of question the wisdom, the what is known around us, and keep an open eye for unexpected phenomena. And then, particularly, I think astronomy is a field that's driven by an observational approach. Most of what we know about the universe comes from going out and looking up at the sky and using telescopes, and it doesn't come from theory. And so, as an observer, I think it taught me that the more tools I have, the more kinds of telescopes I know how to use, the more techniques, the higher the chance of discovering something unexpected, and then being able to recognize and pursue that opportunity. So I think that's been kind of one incredibly valuable lesson that I try to pass on to my own students these days and my postdoctoral fellows. The other thing is really this discovery related to the first neutron star collision. That event was so incredibly rich in terms of the amount of science we could glean from it, from one singular event. And again, I think because my research group was so well prepared and knew how to use all these different techniques, how to combine information from gravitational waves and from light, and use radio telescopes and gamma ray satellites and all of these techniques, we were really able to put together a complete picture of what happened in that event, all the way from the final seconds before those two neutron stars collided to many days and months and even years later. We are in fact still studying that source. Even now, 3.5 years later, we can still detect a faint glow of radio and X-ray radiation from it. And so being able to kind of put together all these pieces into a complete picture that combines information from light and gravitational waves is incredibly rewarding. And I think that's, in many ways, that's the wave of the future of astronomy, is being able to use these tools in a combined way to go much deeper in our understanding than what we were able to do before.
that is extremely, you brought up several things I just would like to recap on. And one is that you early on confronted preconceived notions, and you realized that you, because you were young and inexperienced, you took a risk that many people would not take. But these are extremely important in science, and it happens on a regular basis, and we never seem to learn. But it's probably you are very sensitive to this in your own students, that you can see that they need to take a risk, they need a little encouragement, and to try not to have the preconceived notions. And the other is that some of these discoveries just went on and on with the information, with new information. And another thing that you brought out was the combination of approaches or techniques or equipment, whatever, that this is going to be extremely important in the future. And so people like you have to be kind of open to learning all the time, I guess, how to do this approach. The other thing then is, what are your expectations for the future given all of this most interesting background?
Yeah, I think that the future is really exciting in the sense that we have all of these new facilities that are coming online either now or in this decade. So obviously the gravitational wave detectors are still being upgraded. They have not reached their full potential yet. And so the number of sources that are going to be detected through gravitational waves is only going to grow year to year. Right now, it's their number in the tens, and it's going to be soon in the hundreds. And then the next generation of facilities is already being planned. And the goal there is to build gravitational wave facilities that are so sensitive that they will essentially see every black hole collision that ever happened in the history of the universe. And so this field is just growing exponentially. So that's one direction that I think is incredibly exciting. In the kind of more traditional astronomy, we have more and more powerful telescopes being built both on the ground and for space. The James Webb Space Telescope, which is the successor to Hubble,
this year.
This year, yeah, or this year, sorry, and it will, in fact, have capabilities that are particularly interesting for the question of studying the origin of heavy elements. It is designed for infrared observations, where the signature of formation of heavy elements is the dominant one. And so our hope is to use the James Webb to study gravitational wave events, to follow up on sources discovered by LIGO. And there are many other facilities that are being built. So the capabilities are just growing dramatically. At the same time, we're experiencing, like every field of science or of human endeavor, these large data sets and the use of machine learning and artificial intelligence in astronomy is now becoming more pervasive. And I think the area of studying gravitational waves is another arena for those kind of techniques to continue to flourish and to help us gain a deeper understanding of the data. So there are all of these things happening at the same time. It's going to be a really exciting decade.
I think so. It does sound like you really are on a new frontier in terms of the possibility of answering some of the big questions about the cosmos that you couldn't answer without you bring out the big data sets. This kind of the kinds of observations that are possible now. These international collaborations. Another one, I suppose. But it sounds so exciting for the future. I hope we survive in time to enjoy it. We seem to go down in one area and then we triumph in another area like yours. Dr. Berger, I appreciate so much your giving your time. It was really interesting to speak with you. I wish we had a little more time to go through some of these interesting signals more, the waves, the different types of waves, maybe another time. But in the meanwhile, thank you very much for wonderful information and for reaching out to the public. Write another book, this one for the real public.
Sure. Thank you very much for taking the time to talk with me and for the interest in this area, which I think is really really revolutionary.
Oh, this is very exciting. Thank you.
Thank you very much.